So we're spending our second day on buffer problems. And before we were using the Henderson-Hasselbalch equation and just using it to, we were given the concentration of the conjugate acid and the conjugate base for some buffer system, some weak acid, and then we just went straightforward kind of and calculated the pH of the buffer using our Henderson-Hasselbalch equation. So what we're going to do today is kind of the same thing, except perhaps a little more applicable if there's two types of problems. One is we want to know how much acid or base to add to adjust the pH. You could be making a buffer, and remember in those steps to make the buffer, you had to add some NaOH or some HCl to adjust the pH to get it to where you want, and then once you got it there, then you filled it up to the mark with water, and you essentially made your buffer. So just how much acid or base should you add? That could be a question. Or, dang it, we have this nice system and we want our enzymes to keep doing their job, and it has to stay at this pH, and some acid or some base got in there. Oh, what's going to be the new pH? Is this stuff going to keep working? What's the new pH going to be? So there's really two types of questions. And regardless of what the type of question is, we're going to prepare a mole table. So identify the reaction that's going on, and we'll prepare a mole table. Mole meaning it's just ice, except we want everything in terms of moles and not concentration. So that's why I call it a mole table. And then once we figure out from our reaction and our ice mole table, we'll figure out the moles of A minus, the moles of HA, plug it in, and find what we're looking for. So let's go ahead and get started. Here's our first question. And is it the same as on your sheet? It is. Good. Okay. How many mils of 0.289 molar nitric acid or 0.32 molar sodium hydroxide should be added to 128 mils of 0.078 molar ethylamine to give a pH of 10.78? Okay. So the problem that makes this a problem is this guy right here. I mean, it's a weak system. So that means you have to do some calculating, right? So how do you do this? Mole table, right? But first, we need to identify the reaction. And to identify the reaction, you have to know, which one is it going to be? Is it going to be this one or this one in the first place, right? So, and remember, it goes back to our last class period, the names of these buffers, these weak systems. They always correspond to the what form? The neutral form. So, I don't know, maybe your brain is better than mine. You remember ethylamine from, Friday. Oh yeah, that was if you don't, well, you're like me. I've done this multiple times already. I'm going to go back. I'm going to find the table, right, with ethylamine in it. Whoop. So here's ethylamine. Let's pick on Andy. Okay. So by using this table, we should know whether ethylamine, you pull off the shelf, right? Ethylamine, it's a neutral compound, and we're pulling it off the shelf. It will react with NaOH or HCl. Which one would ethylamine react with? It should react with NaOH. Everybody agree? Everybody agrees? Ethylamine is a conjugate acid or a conjugate base? It's a conjugate base, right? Because to make it neutral, you have to rip off that guy's acidic hydrogen, right? The acidic form has a plus. Can you see that? The acidic form has a plus. So to make ethylamine, you have to rip off a hydrogen. So ethylamine is a conjugate base. Conjugate bases will only react with Acids or bases? Acids. Right? So acid is what it's going to react with. So we go back to our reaction here, and you can write it out. If you're more comfortable doing this, you can write it out as CH3, CH2, NH2, right? That's exactly what ethylamine is. And it'll react with our acid to form CH3, CH2, NH3+. Okay? So you can write this reaction, or since you're just making a mole table, it really doesn't matter as long as you have the right format. You're identifying a conjugate base, reacting with an acid, forming the conjugate acid. What general term have we been using for a conjugate base? For conjugate base, A minus. So couldn't we just write A minus plus H plus gives HA? It's either one works. Whatever makes the most sense to you is what you should do. Either one works. They both work. And if you prefer writing HNO3 instead of H plus, that works too, right? I just like writing H plus because nitrate's not doing anything. Okay. So, but however you like to write your reaction, you need to make a mole table. But it starts with writing that reaction that controls the pH. That reaction that illustrates what's going on. So we started by identifying what is ethylamine. It's got to be that neutral form has to be a conjugate acid or conjugate base. We looked at the table. We saw that it was a compound that had a plus on it. Ah, dang. That means that you got to remove that hydrogen. The name corresponds to the neutral form, so the name for ethylamine is going to correspond to the conjugate base. Everyone following me so far? Jeff, you following me? Okay. So that's how since whatever this is, whatever we're starting out with, as this is the conjugate base, it's only going to react with the acid. So that's why we wrote this reaction. And if you're more comfortable writing the general form of the reaction, that works too. You don't have to worry about all the 2's and 3's and numbers of H's and everything. Okay? All right. So let's see if we can fill in this mole table. A mole table. Yes? Question? No, please ask.
Well, we're looking at an acid dissociation constant. So is ethylamine
Ethyl.
acid and it's plus sign is telling us to?
Ethylamine, how they, let's go back here, day 27. So what they did, this is their way of doing it. So we just have to live with the author's way of, but it's a conventional way. So you're right, these are Ka tables. So, and Ka is for HA, weak acids. So that means, in that sense, they're kind of consistent. All they're listing are the acid forms. And whether they exist in a bottle or not, it doesn't matter. They're giving you the structure of HA every single time. However, that's not how we name them. And that's where this gets really confusing. And it may not be the best way to do this. Because look, here's the name, but that's not the structure. Right? So it's very confusing. It's a very good question, because that name does not correspond to that structure at all. Do you see that? It's a very good question. This structure is always for HA. Now, if it's always for the conjugate acid form. If it has a plus on it, that's not the name of the compound. That's not the name of the compound we're interested in. The name always corresponds to the neutral form. The name always corresponds to the form where you can just pull it straight off the shelf. It says ethylamine on that bottle. Okay, it says ethylamine. But that's the conjugate base, because the conjugate acid has a plus on it, according to our table. So be really careful. Really careful. Do you have a question, Mike?
I was going to ask, like, the formula you had, like the H plus, well, A minus whatever plus H goes to HA.
Yeah.
How come you didn't write it backwards? Like, you know, like how come you didn't write
Oh,
it
because, oh, sorry. How come I didn't write the Ka reaction? Where'd it go? Day 28. Okay, so you're asking, why didn't I write the Ka reaction, right? The Ka or the Kb reaction, right? What we want to do is identify, because the reason why I wrote it this way is to illustrate what's going on. Because we're starting with this. So that means we're starting with this compound, or we're starting with this compound. They're chemically equivalent. The conjugate base, we're starting with it. And then we're going to add, right, some HNO3 or NaOH. So since to give a pH of 10.6, so we're adding this, acid or base. So you're always going to do these problems right here. You're either going to add the acid, it's going to be a strong acid, or you're going to add, instead of H plus, you're going to write OH minus, right? That's how it's going to look every single time. So we can keep track of these things, and we can figure out, here's our conjugate base, here's our conjugate acid, and it's nice because it's in moles. We can plug it right into our Henderson-Hasselbalch equation, because that's all we need is, right, remember that equation? pH equals pKa plus the log of the moles of the conjugate base or the moles of the conjugate acid. So that's why we do the mole table. And all we're interested in moles of conjugate base, moles of conjugate acid, so we can plug in there. Okay, so we'll get it from that column and that column. Okay, so I need to start somewhere, probably that initial row. Let's pick on Monica. Can we put anything in that initial row?
And would you solve for the moles of ethylamine?
Yeah, we need the moles of the ethylamine has to go in this table. The moles of the ethylamine. And how do you get the moles of the ethylamine, anybody? You don't need a mole bridge. Just multiply volume times concentration, right? Because they told us the trick is knowing what ethylamine is. Is it the conjugate acid or conjugate base? Because we know the concentration of it and we know the volume of it. So we know the moles. 0.128 0.128 liters times 0.0078, whatever number that is. There's our initial moles of conjugate base. Yeah, because you have to convert it into liters. So divide it by 1,000. So move the decimal place over 3 places. It'd be 0.128. Is there any H plus initially with this? No, because the concept here is all you've got is ethylamine. Okay, how much nitric acid do we have to add? So initially all you have is ethylamine in that beaker, 128 milliliters of it. So nothing there initially for the H plus. Is there any conjugate acid form there initially? No. Why not? Why not? There's nothing there initially because remember the name corresponds to the neutral form. So I mean that's all there is. When you pull off that bottle of ethylamine, you have literally a bottle of pure conjugate base. That's all. You have no conjugate acid there. You have a bottle of pure conjugate base. So that's what ethylamine is, because that's the neutral form. So you have absolutely no conjugate acid there. The name corresponds to the neutral form. The change row. What do we do in these ice tables for change rows, Gloriana? Put in negative x's and put in? Yeah, same story. And it's nice because, again, we wrote the reaction that corresponds to what's actually happening. So the negative, I should write negative x here, right? The negative x's, right, they're supposed to be reacting. And then they're supposed to be being produced over here. So a negative x for H plus may not make a whole lot of sense because, right, aren't we supposed to add these guys up? It's 0.128 times 0.0078. 9.984 times 10. Thank you very much. 10 to the negative 4 minus x. All right, and that would, so I don't know, you can just kind of erase that. I mean, this has to be, these are just amounts. I mean, if you like to have the minus, it's not hurting anything. The point is that x is going to be the moles of that HNO3 that we have to add. Right, because that's what x is going to be. X is going to be the moles of the HNO3 that we have to add. Okay. And then if we know the moles, so we'll solve for x, right? Because that will equal the number of moles of H plus. And then how do we go from number of moles of H plus all the way to that mils? Right? Somehow we'll figure out what x is, and then how do we go from x, from these moles of H plus, to mils of our answer? Use the molarity, 0.289 moles per liter. So that's how we'll get there. Okay, so that's the big picture. The big picture is get x, because that'll be the moles of H plus. Convert those moles into milliliters. Well, I convert it into liters first, then convert it to milliliters, using the molarity of that HNO3. Okay, so we got to solve for that, find that x. Okay, Ida, how do we substitute into this Henderson-Hasselbalch equation to solve for our x? What would you put where? Okay, the pKa. Oh, we need that table. Shoot. I already lost it. I think this is it, right? 10.673 is our pKa. Okay. So let's get 10.673 in for that. .673. Then anything else, Ida, that you see? Yeah, but it has to be minus x though, right? Yeah, so that whole, whatever's in that E row are the moles at equilibrium. So this is what we're going to be substituting in. So the whole 9, like she said, the 9.984 to 10 to the negative 4 minus x goes in for A minus, for the conjugate base. And keep going. Kelly, keep substituting in here. What else can you substitute in? Put the x in for? Good. One more thing here, Kimberly. What else can we substitute in? We're still missing this guy. Yes, the 10.78 is a final pH. Okay, no worries, because Sabina's going to tell us how to solve for x. What would you do first?
You move the 10, we move the pKa over.
Yeah, good. Move the 10.673 over. Good. Okay, then what?
Would you have to take the ln of the opposite one?
Here's the, this is what she's got to remember. Everyone has to remember. What's the inverse function of log? So that you can raise this, both equations to this, and then that log disappears. Raise it to the 10. If it was little ln, you have to raise it to the e. Yeah. Okay, so bring the 10.673 over, raise both sides to the 10 power, and you're getting really close to solving for x.
Dr. Smith, do you say 10 to the power on each side, or each side to the 10 power?
Each side has to be to the 10 power.
I thought it was 10 raised to the
10, so you're going to raise 10, take 10.78 minus 10.673, whatever you get. It has to be 10 to that power, and then 10 to the log of this thing, but the log and the 10 disappear because they're inverses.
10 to
See what you get. Danielle, did you get that? Okay, now how are you going to solve for x? Yeah, good. Bring this x over here. Then what? You want to see it? Then combine the x's. Bring that, like Danielle said, bring the 1.2 x over with the 1.28, right? Multiply both sides by x. And then combine the x's. Right? Because you have an x term on both sides then. Combine them, and then solve for x. Let's see what you get. Yeah, because you get 1.28x equals this number minus x. So then add x to both sides to combine the x's. Or subtract 1.28x from both sides, whatever. I think it'd be easier to add x to both sides.
X is going to be our molarity?
Look at the table. It tells you what x is.
I got 4.38 times 10 to the negative 4 for x. You did? Okay, good. Yes, 4.38 times 10 to the negative 4.
Okay, repeat it one more time. What did you get for x?
4.38 times 10 to the negative 4.
Okay, and then Jeff, you said you got that too? Okay. So I had to, so this part makes sense, right?
Yeah.
Okay, so yeah, I had to combine the x's. So either I can add a negative 1.28x to both sides, or I can add x to both sides. Either way, it doesn't matter. You'll solve for it. So I just added x to both sides. So plus x and plus x, so I end up with 2.28x. Because x plus 1.28x would be 2.28x. Just add the coefficients.
Okay.
Right? So right. Okay. So we'll get your x, recognize what it is, and then calculate the final answer. Yeah, so 1.28 times x plus x, so combine these two, and then divide both sides by 2.28.
I don't understand how you're combining them.
Because it's kind of like a plus 2a is 3a.
So you just added.
Yeah, so just add the coefficients. So it'd be 1 plus 1.279. Yeah, because there's a 1 in there. We're always too lazy to write it.
Okay.
Desiree, you got this for your x? Then what'd you do? What'd you do next? Because this number has what units? Moles of H plus.
So you would divide it by the molarity?
Yeah, if you do the box thing, and then you don't screw up whether you multiply or divide. Mole has to be on the bottom. Liters would be up on top. If I don't write it out, I end up screwing it up half the time. look up in the problem to see what the molarity is. Right? And we're adding acids. That's the 0.289. And then, Brandy, what'd you get?
1.52.
1.52. Anybody else?
Yeah.
Oh, we got a lot of takers. 1.52. So you had 1.52 milliliters of that nitric acid, and you'd adjust the pH to 10.78. It'd be a lot easier than randomly doing it, but okay. So again, what we did first is we identified what the compound is. Does it correspond to A minus or H plus? Or sorry, A minus or HA? Has to be one or the other. It always corresponds to the neutral form. And if the neutral form corresponds to the weak acid, well, then you're going to be adding NaOH. So you'd write the reaction HA plus OH minus, right? Forms A minus plus water, something like that. Does that make sense? Let's write that one. Let's say it did correspond to HA. Then it's going to react with OH minus, the NaOH, to make what? What mole table would you write? H2O plus A minus. Right? You see that? Because that H grabs onto the OH minus. There's your water. And all that's left over is A minus. Okay. So that's the other possibility. Those are only two. Okay. Ricky, you got an idea on this one? Write the chemical reactions whose equilibrium constants are Kb and Ka for imidazole and imidazole hydrochloride, respectively. They want the reactions. Where would you start with something like this?
You would want to look at the table.
Look at the table so that...
What do you have, a base or an acid?
Yeah, not only to find out... Yeah, look at the table so you can see what the structure is, unless your organic is a lot better than mine, right? Look at the table, see what it is. So let's start there. He says start the table. That's a great suggestion. Well, let's back up. Let's make sure you see the big picture first. When they say write a Kb reaction, it better be of what form? Gloriana. Well, how did we write our Kb reactions? We always said what? In general. How do we generally write them?
It's the acid and hydroxide on one side, on the left side. So like H2O there.
Well, how'd you start with the reactants? How do you start with the reactants on a Kb reaction?
How do I start with the reaction?
Yeah. What are the reactants on a Kb reaction?
HA,
Yeah, it's a Kb reaction.
HB.
Someone help her out. How do you write Kb reactions in general?
Base plus water plus
What? How do we write our conjugate base? A minus plus water forms H2O and... Oh, sorry, not H2O. Forms OH minus and... Okay. Burn that in your head, because then you can answer a question like this straightforward. You just have to look up and find out what the conjugate base is, formula, the chemical formula, for imidazole, and put it in there. And it's going to look great. Ka reaction, same thing. We need to have our... Now, this is not the answer. I'm just showing the general form. The general form, Jeff, for a Ka reaction, general, is what goes to what?
HA on the reactant side.
Yeah?
And then H plus and A minus.
Yeah. Okay, so let's find imidazole.
Dr. Smith,
Yeah.
I was going to ask one more thing. Do you even, I mean, for this one, you don't even really need to look at the table, though, right? Because you can see that the imidazole has an H plus on the end, and that's why the Cl sticking to it in the first place.
There you go. He's getting the hang of this. Do you see what's going through Ricky's head? Do you hear what he's saying? He's saying that you really don't need to look at the table, if you know what imidazole is, because one is a hydrochloride form. And what does that mean? That means it's got a big chloride negative, a chloride anion hanging onto it, right? So everything else has to be a plus. That's going to be the acidic form. So you're going to have this acidic form with a Cl minus on it. In other words, let's look at the table. It'll be easier. What you're thinking is exactly right. Imidazole. What the heck? Something just died on me. And I lost everything. 27. Wow, I didn't lose it. I need a day 27. Here it is. I have to go all the way down to the I's. H. Here's imidazole. Okay. But this is really what we're interested in, right? The structure. Does it have a plus on it? Look again, Kimberly. Well, then sit up closer. Kick Desiree. Get here earlier and get her chair, right? So it has a plus on it. It has a plus on it. So the hydrochloride just means that would be the structure, right, for imidazole hydrochloride. It would be the conjugate acid form with a chloride anion hanging onto it, just like what Ricky was saying. Okay, so our HA is right there. Here's our HA form. Right? So when we wrote the Ka reaction or the Kb reaction, wherever you saw HA, this is what you write. The Kb, the A minus, would be what? Draw that exact same structure, but just what's missing? H plus is missing. So to make it neutral, lose that H plus. Okay, so go ahead and do that. Write the Ka and the Kb reaction. For imidazole and imidazole hydrochloride.
So would you like us to draw some of these, or draw these when we do the Kb?
You have to. You don't have any choice.
Right?
You can't write A minus
What do you write?
because they
Imidazole?
you have to. That's where the table would come in handy, even if you recognize it as a conjugate acid. If you don't know what imidazole is, and I don't. I use a table. Why memorize this kind of thing? Just Google it. Or use the table. If I can select the whole thing. Yeah, I can't copy it. So then it's from the table. Okay. Does that make sense? Let's jump down to part B. Find the pH of a solution prepared by mixing 1 gram of imidazole with 1 gram of imidazole hydrochloride and diluting to 100 milliliters. Calculate the pH of a solution where we're adding 1 gram of imidazole and 1 gram of imidazole hydrochloride, diluting to 100 milliliters. Marlena? Does this sound like, ooh, we should write a mole table? We just got done doing a mole table thing. Sounded like the answer to everything. But no, she's right. Right? Because we're not really doing anything. We're not reacting anything. Right? This should be a straightforward, whose equation? What's the name of the guy? Henderson-Hasselbalch. It's a straightforward Henderson-Hasselbalch equation problem. pH equals pKa plus the log moles of the conjugate base all over the moles of the conjugate acid. From the table, we can get pKa. We just got to plug in the moles of the conjugate base and the moles of the conjugate acid. So how are you going to get, Desiree, the moles of the conjugate base and the moles of the conjugate acid? Okay, we're going to look at that pKa first. 28. Let's see, that was this guy. Not him. This guy. 6.993 is the first one, so we'll just do 6.993. Okay, Danielle, how do you get moles? Oh, we looked it up in the table for imidazole. That's the pKa. Yeah, either one, moles of HA or moles of A minus. How are you going to get it?
So divided by,
Yeah?
or by the 0.1.
Divide the 1 gram by, what's the word? How do you convert grams to moles? Molar mass. So we just got to figure out what the molar mass is of this compound, figure out what the molar mass is of this compound, and convert grams to moles.
I got 68.082 for imidazole.
What's your chemical formula for it?
I got C3.
Wait, hey, hang on. Let me go back to the picture, and so then we can count and see if you were doing it right. Okay, so here he is. Let's see here. Pick a color. Okay, so you said C, how many?
C3.
C3,
N2.
N2,
H4.
H4. And that is our imidazole, right? That's our A minus?
Yes.
Okay, does everybody agree to that? So he's saying that this structure is that, right? Oh, look at that. I didn't draw this very well. Look how mine looks bent there. That should be a straight line. So do you count 3 carbons? I count 3 carbons. 1, 2, 3 carbons, right? I think a trick is the hydrogens. Are there any hydrogens right here? Yes. How many? 1. Because each carbon has how many bonds? 4. So there's definitely one there. That means there will be definitely one here or not? Yes. Yep. In here?
Yes.
Yep. So it's getting to be a job, right? H. Okay. And then we're done, right? So here's our 3 H's. I agree. Oh, he has 4 H's. Oh, there, I didn't count that one. Right? So 1, 2, 3, 4 H's is 2 N's. Makes sense, right? So if that's A minus, what do you propose HA is going to be? What chemical structure, Jackie? So just add what to this, and we'll have it. One more hydrogen. Here's where the trick question comes in. And chlorine, because it's hydrochloride. That's how you get that chlorine on there. If you don't have a chloride on there, it's not neutral. So you can't make a bottle of it, and you can't mass it or nothing if it's not neutral. So it'll be the exact same thing. C3N2H4. But then it has to have also the hydrochloride, another H and another Cl. So, because if you don't add both of those, you're going to get the wrong molar mass. You get the wrong number of moles then. So find the molar mass of both imidazole, the conjugate base form, and imidazole hydrochloride, the conjugate acid form. Okay. So the imidazole, did anybody get the molar mass of that one? The A minus? 170?
No, I'm sorry, just 70 for imidazole.
Just 70 for imidazole?
Yeah.
Anybody else get 70 for imidazole for A minus? 68.4. I see here a lot of 68s.
Yeah,
Yeah, I just-
68.082.
I just rounded.
Oh, don't round that much. You're not going to get the right answer.
I was in a hurry. Sorry.
Okay. Okay, now you have to add an H to it and a chlorine, then you get imidazole hydrochloride. Now the molar mass is 104.54, I hear. Okay. And then you do all the math, and then you get your answer. Okay. Let's just talk about this last one before we let you go. Calculate the pH of that solution if 2.3 mils of 1.07 molar HClO4 are added. Okay. There's an easy way and a hard way. I think the easy way is to forget the whole kind of mole table thing and just jump right in to our Henderson-Hasselbalch equation. Okay, so what we're going to do is first recognize we're adding an acid or a base?
Acid.
We're adding an acid. So that acid, will it react with A minus on top, or will it react with the HA on the bottom? Acid will react with the base, right? So it's going to react with it. So this is going to be so many moles, right? That'll be 0.0023 times 1.07. Right? That'll be the moles of H plus. So my moles of A minus is going to go down or go up? My conjugate base. It's going to go down. It has to, because it's reacting with the acid to keep the pH the same, to buffer it. So I have to subtract those number of moles. That number right there. With the conjugate base, right, it reacts with this acid, and it ends up forming the conjugate A minus reacts with H plus and forms HA. So I'm going to be adding those moles here. Well, what numbers go here and here? Danielle, what numbers am I going to put here? You're looking up there. I think you're seeing it. The initial moles, right? The initial moles. So whatever we got here, our initial moles, whatever we got here, there's our initial moles of base. Here's our initial moles of the HA. And then we'll get it. Okay. So you just have to recognize, oh, is the conjugate base or is the conjugate acid going to form? Sorry, yeah, is the conjugate base or the conjugate acid, is it going to react with what we're adding? And then you just add or subtract those moles correspondingly. Okay?
So, is there going to be subtracting from the top?
The reason why I subtracted from the top is because remember the Henderson-Hasselbalch equation has the conjugate base up on top.
Okay, so you subtracted
Yeah, because the conjugate base is going to decrease in moles. Because it has to, because it's going to react with what I'm adding, the H+.
adding the same, you're increasing the concentration?
No, because what we're doing is this buffer system has an acid, a strong acid being added to it. And if something doesn't react with this strong acid, the pH is going to change. So something has to react with it. What reacts with it? The conjugate base.
Okay, so but isn't H plus, isn't Henderson Hasselbalch log of A minus over H?
A minus over HA. So that's why this is your starting point.
Right, that's when
Mhm.
the concentration of perchloric acid goes at the bottom? Or what
I-
goes at the bottom?
What goes on the bottom is the moles of HA. How many moles of HA will you have? Well, you have your initial, which we calculated from part B. You have your initial, but then we're going to have a little extra because this A minus is getting converted into HA. So that's why we have to add on the moles, the strong acid number of moles,
Right.
because that's the amount that's going to be added. It's going to increase. The moles of HA is actually going to increase a little bit.
So we do put the concentration of perchloric acid in.
There's no concentrations here. This is moles.
Oh, I mean,
Moles of HA plus the moles of H plus that we added. The moles of HA that got created. Does that make sense?
Yes, sir.
Explain to Gloriana.
So what I think with that is that since you're adding H plus, you have to add it to.
So we have to convert 1.07.
How do you convert this to, how do you get this to moles? Well, it's multiplied, but this has to be in liters. So this is moles of H plus. So whatever number that is, you got to subtract it from the moles of A minus, and you have to add it to the moles of HA. Because A minus is getting converted to HA.